class, not including the last week where you'll do your presentations, but this is the second to last week where we're actually going to learn stuff. So today we're going to be doing algorithms, and then we're going to have a guest lecturer doing mobile dev. Okay, so first of all, let's do the attendance quiz. So make sure to do that right now. I know last week or a couple weeks back there were some complaints about I didn't do it in time and you closed it, but like we give you time right now to do it, so make sure you go ahead and complete that. Okay guys, go ahead and finish up the quiz. Is anybody not done? Okay, I'm going to assume everybody's finished then. We're going to move on. Alright, so homework 6, it was released yesterday. It's going to be due next Tuesday at 11:59, so that's going to be the last homework. And this one's a bit of a short one, but you might want to just get started on it early anyway in case you run into any problems. So just be aware of that. It's going to cover some of the stuff we talked about last week and stacks and queues again. Okay, so with that in mind, we have office hours Monday, Wednesday, and Thursday next week. So actually Wednesday and Thursday, we might end up canceling because there will not be homework after that point. But definitely Monday office hours, if you need help, go ahead and come in. Okay, and then just another reminder about final presentations. So they're going to be Tuesday, May 1st in the atrium. It's going to be a science fair style, so you'll have a table. So each group is going to get their own table this time, and we're going to have food too. So basically we're going to advertise to other people so that they come get free food and then see what projects you guys are working on. With that in mind also, you guys can have posters that explain your projects. So you can ask your PMs more about that. We talked about it at our staff meeting. So if you want to make posters and have like a nice size poster for your project, then definitely go ahead, because those always look really nice, and we can always use those to advertise for in the fall, like the different cool projects you guys have done. Okay, so yeah, here's our emails, and now we're gonna go straight into algorithms. So, okay, so we have Victor here to present algorithms. All right, I feel like the atmosphere in here is very unenthusiastic. You have to make this more enthusiastic now. I kind of just trailed off at the end.
Hi guys. I'm so excited to be here today. So I'll just take a second to set myself up, sorry. So how's everyone's semester going? Alright, so I know this is supposed to be algorithms, but you know, what exactly is an algorithm, right? That was a rhetorical question, I guess. So this lecture is actually going to be sort of like a mix of a lot of things. Namely, there's going to be complexity theory, and then there's going to be real life stuff, and why complexity theory doesn't really work in real life a lot of the times, but it still does, so you should learn it. And then there's also going to be a section on, like, I guess, practical interviewing. This is my version. I guess not, so I have to, oh, excellent, it is on. Alright, so let's talk about complexity theory first, I guess. So, I'm sure you guys all have like sort of some concept that problems are hard, and so is life. But some problems in life are harder than other problems in life, right? And that's how we come up with this, you know, like concept of how hard exactly is a problem, right? And the good thing about computer science and math is that we can actually quantify how hard a problem is, so we know whether to give up early or not. God, I'm trying so hard to like make these jokes. I'm just getting nothing, so I'm just gonna stop making jokes and. But anyways, you know, so like a problem like sorting a bucket of fruit by its weight versus, you know, what should I eat for lunch today, are, you know, different classes of problems. In the case, you know, like sorting fruit buckets by, I didn't come up with this, by the way, this is someone else's notes. The beginning is, I wrote some too, don't worry. But, you know, sorting, you know, a bucket of fruit by weight is very objective. You can just, you know, grab the bucket and weigh it and then, like, you know, put it in order. Whereas, you know, maybe the line in Chipotle is really long, maybe I don't want to walk that far, maybe I'm feeling like eating pasta, or like I just want to cook food at home. There's all like these different variables that go into solving the problem of what I should eat for lunch, versus, you know, just one judgment for sorting a bucket of fruit. I don't know why the bucket of fruit. Okay, let's talk about Big O though, before we dive into like all this stuff. So, have we actually had like sort of a concrete discussion about Big O? Or has it sort of just been floated out there?
It's in 125.
Okay, good. So like, you guys sort of have this like concept of you know, things can take more time or less time to run. And in general, here's like the scale of like fastest, you know, constant time things, to slowest, which is like, you know, n factorial, which is something you never want to do because then it'll just never finish running. What we're really interested in is this one right here. Polynomial-Time Solutions. So, you know, n to a constant factor, you know, n squared, your n cubes, you know, and at the, you know, on that level, sort of, what constant doesn't really matter at a certain point when you're comparing it to exponential time, which is a constant to the n, so like 2 to the n, or 3 to the n, or et cetera, right? So then that's what sort of like complexity theory is based on, I guess. Like those are the most important like time factors that we want to consider when we talk about complexity theory. And here's like a nice picture of, you know, some stuff we'll talk about. I'll come back to it actually. It probably doesn't make much sense, but you know, you have like a comet looking thing and you have an eyeball looking thing. And of course, you know, we don't always measure things by just how fast or how complex it is. We can also measure like, you know, how much memory does this program take to run, how much, you know, how big is the program itself, a bunch of other things, but like in general, we want to measure how fast it runs because that's like, you know, the limiting factor for a lot of things. And there's a lot of problems that you can talk about, you know, space constraints for problems. I think recently there was a really cool thing. Like, have you guys heard of 6K intros? Where it's like people trying to like make rendering, like they make like really cool renders and like animations using only like 64 kilobytes of memory. And like I think the recent winner of this one contest was like this guy who made like, or these two guys that made like this super like detailed like submarine journey, and there's like water graphics and it was really cool. So like that's an example of like space complexity would be cool. I'm sure it was really inefficient because in order to fit, you know, such an animation in like a small binary, you have to like do a lot of real-time computing. So you gotta like, you know, run the simulations, and it probably has to unpack itself as well, stuff like that. But enough about space complexity, because we're talking about time complexity. So let's talk about like, you know, there's a lot of words here that you might have heard of, you know, like NP, NP complete, P is equal to NP. Have you guys like, you know, heard of P equals NP? Because if you solve it, you'll probably be like the most famous person in the world, at least for a few years. Well, actually for all time now, honestly, because it's like pretty important. But like, you know, what do all these like letters and whatnot mean? Right? Because like, it's like hard to understand when you first like get into it. I know I was like super confused. So let's just sort of talk about what this stuff means, right? So first of all, we have, so all these letters, NP hard, NP complete, NP, and P, correspond to like problem classes. And a problem class is sort of just like a set of problems that are classified under like this label of P. So first of all, for P stands for polynomial time, and P is just the set of all problems that can be solved in polynomial time. All right, that's pretty easy, right? So say like, you know, I give you an algorithm and I want it to run, or I give you a problem and I want it to run in like, you know, n squared time, right? So if you gave me like, you know, a solution that was like n squared or n cubed or whatever, that'd be polynomial time. You know, there's a lot of algorithms that are just polynomial time, like sorting algorithms, or you know, most of the stuff we do. So generally they're like pretty easy problems. What I guess really smart mathematicians care about are the harder problems, which we start to get into with NP, which stands for non-deterministic polynomial time. So what NP is it's a set of all problems that can have their solutions verified in polynomial time. So it can't be necessarily solved in polynomial time, but if I gave you like an answer to a problem, then you could say, okay, this answer makes sense, and I can like, you know, prove that it makes sense in polynomial time. And this is sort of like, like this stuff is like sort of like confusing, so if you have any questions, like just raise your hand and ask me right away. Alright, but I'll try to like give examples so that like it's a little understandable. So do you guys know about like graph coloring? No? Okay, so do you guys know about graphs? Yeah, so you know how like a graph is just like a set of nodes that are connected to like other nodes? So say I wanted you to color the graph. So I want, you know, each node to have a color, and the constraint is that you can't have the same color. One node can't be the same color as a node that it's touching, right? So say like, I give you this big complicated graph and I'm saying, okay, so I want you to go through the graph and like color each node such that I want you to use the least number of colors possible, and I want you to make sure that each node is not the same color as the node it's touching. Okay, so that's like sort of that's an example of an NP problem, where if I wanted you to do this, you can come up with an exponential solution where the exponential solution is literally to try every single combination of colors for the graph, which understandably takes a really long time. But if I gave you like a graph and I gave you like a picture of a colored graph, you could look at it and be like, oh yeah, this makes sense, right? Like I can see that, all the nodes are colored according to the rules, and that was like very easy to verify. Does that sort of make sense for what an NP problem is? So it's like, if I gave you a solution, you could tell that it is correct in a short amount of time, versus if I asked you to find a solution, it would take a long time, right? So the cool thing is that polynomial, so let's just look at this side of the graph first. So you can see that like polynomial problems in P are also an NP just because they're easy, and NP is like hard, but it also contains like easier problems such as the polynomial-time ones, right? So that's what like generally what non-deterministic polynomial time means. If a program is or an algorithm is non-deterministic polynomial time. Does that make sense to everyone? Have I lost you all? No? Good. Excellent. It took me years. It took me years to understand this. Alright, so let's talk about co-NP, which is sort of another thing. It's not as important, really. It's basically the opposite as NP is, okay, so if I give you like a graph that's uncolorable, for whatever reason, I don't know what that means, but like you could verify that like, the graph is uncolorable. Or like, you can verify that there is not a solution in polynomial time. That's all co-NP means. It's basically the opposite of NP. You can see that it's not actually in this, but I just wanted to mention it since it's sort of important to mathematicians. So then the next big thing is NP-complete. And NP-complete is basically the set of problems that all the problems in NP can reduce to. So what does that mean, right? So say we have like, let me think. So say, here's like a really dumb example that might not make any sense, but hopefully it does. Say I give you 2 graphs. I tell you to color 2 graphs. You could reduce that technically to coloring 1 graph. So you can see that coloring, well actually, so I'll just tell you straight up right now, like graph coloring is a problem in NP, and so is like the traveling salesman problem. That just means that, say I give you like a different problem involving graphs, given some like, fancy graph manipulation stuff, you could reduce it down to like the graph coloring problem. Or if you had a solution, if you know how to if you know how to verify the graph coloring problem, you can also verify the problem, right? So basically, NP-complete is sort of like, you can think of it as these like model problems, or like the epitome of NP, where, these problems, if these problems are solved, you could probably like, or if these problems are like, when I say solved, I mean like, find a polynomial solution for it. So if these problems were like, figured out, then you'd also just figure out everything else in NP. This is like, again, this is like confusing stuff. It's hard to explain. I'm sorry if I'm doing a bad job. Are we sort of clear on what NP-complete is? Sort of? Kind of? But like generally when you like talk about NP problems, or like, complexity theory in general, when you're talking about like, problems that are in NP, people will like default to going to like and talking about NP-complete problems just because they sort of epitomize problems in NP, basically. Where you can reduce any other problem to an NP-complete problem. So now with like this sort of background knowledge in mind, we can start talking about P is equal to NP, which is like the point of this graph right here, or these like, pictures. So if the set of, if P is equal to NP, then like the set of problems that are solvable in polynomial time are also the same problems that are solvable in non-deterministic polynomial time. So what does that mean exactly, right? So that means that, sorry, I gotta look at my typed up notes. So whenever you have a problem which solution is quickly verified, think about graph coloring, then you're guaranteed to also be able to find a solution in polynomial time for that problem. Right? So if you can verify a solution to the problem, you can also find a solution to the problem in polynomial time. And again, when I'm saying polynomial time, I mean like n to the c, not like 2 to the n where that's exponential time. Because right now, like a lot of the problems in NP are solvable in exponential time, but people don't really know how to do them in polynomial time, or they're like incredibly difficult, or like if you want to read Wikipedia pages, which is what I did for this, there's like here, this is for graph coloring. Let me show you algorithms. Okay. So you're like, okay, so we have an exact algorithm. You can see that it is solvable in 2.445 to the n. They go up 2.445 to the n, or like they have all these like exact numbers for like smart people who've come up with algorithms that run in like this time, which is incredibly impressive, honestly. Like, I don't even know how you'd go about like coming up with an algorithm that ran in 1.3298 to the n, like complexity, But if p was in fact equal to np, then you would be able to find a solution to like graph coloring in polynomial time as well. And like, what does that mean for the world? It means that a lot of stuff that was hard is now just like very easy, right? So a lot of like mathematical things that people are trying to figure out are suddenly just very easy to figure out. Right. To give like an analogy, I guess, to like, let me think. So say like, do you guys sort of know how like cryptography works? Basically like, there are things that are very hard to do for computers to do, like factoring like discrete logs and doing like discrete algebra. And that's like the basis of like cryptography. And if the analogy is like, if like whatever equivalent p is equal to np problem is solved for like cryptography, then it would suddenly be very easy for computers to like factor discrete logs. Because it's very easy to like verify that you have a correct solution to like this like math formula, but it's very hard to come up with a solution yourself because it's hard to like factor numbers, or it's hard to like do stuff like that. But like, if you knew that it is, so basically like if this was true in like the cryptography analogy, then it'd be just as easy to factor the numbers as it is to like confirm that your solution is correct. Are there any questions? Long pause. Yes.
So if you were able to solve P equals NP, you could do it with NS. What is like the exact problem to solve? Like how can you
So it's been a while since I've like learned this stuff. I took like the class 374 last year, but I'm pretty sure how you'd go about doing it is figuring out an NP complete, or basically like if you figured out that like an NP complete problem has a polynomial, or like where you could prove that you can find like polynomial solutions to an NP complete problem, that generalizes to mean that you can like in general find polynomial solutions to most NP problems. So I'd start looking at like NP complete stuff. There's actually, I remember looking this up because I was like sort of interested in like thinking about it, but then I realized it was too hard. But there's like this wiki for like unsolved math problems, and there's an entry for p is equal to np, and there's like a bunch of subproblems that if you solved it, it would mean that like p is equal to np. So I'd like look that up if you're interested in thinking about it. Also, you earn like $1 million if you solve it, I'm pretty sure. But that's like the least of your worries, because you'd be like famous for the rest of forever. Alright, so the last thing is NP hard. So you can see like this thing right here. Basically, they're problems that are at least as hard as NP complete problems. So like you can reduce an NP complete problem to an NP hard problem. And like the halting problem is a pretty notable example of an NP hard problem. I won't go like too in depth into that. The main thing is like understanding what P is and what NP is and stuff like that. Yeah.
What is the halting problem?
The halting problem is given like, I think a Turing machine, will it stop?
Like a machine, you said a Turing machine?
A Turing machine. So what a Turing machine is say you have like a thing, like you have like you have a head and you have a tape of like infinite length. And the tape has like instructions that the head reads and then like skips around on. Right? So given like an given like an arbitrary tape, I think will the Turing machine halt? And it's like
How would you determine
that's the $1 million question.
Oh, okay, I get it.
Okay, you're asking me all these NP hard questions. Alright, so are there any more questions about like complexity theory? About like all this terminology and all this weird math stuff that I'm not like super into, but it's interesting to think about. So let's like briefly talk about algorithms then. So basically we want to design algorithms to, run as fast as problems given constraints. Because, how else will we measure how good an algorithm is, right? And also unconstrained problems end up being harder to solve. So here are like, a bunch of things you can optimize algorithms for. You can, optimize for speed, you can optimize to save disk space, you can optimize for like, data structures. Here are theoretical guarantees that's highlighted. What did I just do? So why wouldn't you always go for the best theoretical guarantee? Does anyone have any thoughts? Yeah. Yeah, it might not be realistic to do. And also like, I think the best example of this is Quicksort versus merge sort. Are you guys like sort of familiar with those two? So Quicksort, worst case runs in O of n squared. On average, it runs in, I think, n log n, or, yeah, n log n. And Quicksort, or merge sort, always runs in n log n. But then Quicksort is more widely used. And the reason for that is, average, it does run in n log n, as it turns out, and also it takes up less space, and you can do like, it has like other benefits, like you can switch things out in place where you have to like make copies for merge sort, I believe. Stuff like that. So like, best theoretical guarantees doesn't mean best in practice, which is why we're about to talk about real world stuff. So in the real world, computers aren't like these super like theoretical machines. They work because of like memory, and they work because of like CPUs, and they work because, I guess, like, have you guys taken 233? No, okay. If you guys do take 233, I really like that class, it's great. There's a lot of like very nitty-gritty stuff about how computers work in reality. So let's talk about like a few examples of like, for example, like, again, going back to like the merge sort versus quicksort example, quicksort has like better like in practice features, I guess, over merge sort. So the first example, I didn't write these by the way. I sort of know about them. So vectorization is sort of like, I think in the context of array vectorization, where you would perform operations over an array. So if you guys know the like functional programming, or if you guys know like the Python function map, where it just maps something over an array. So say you have an array of like 1, 2, 3, 4, 5, and you want to just add 1 to each one. So you can call Python map, and you can like pass in like the array, and you can pass in like +1, and it'll just add 1 to every single element of the array. So then you'd have like 2, 3, 4, 5, 6, right? And stuff like that can be done in parallel. So it's like, more optimized. So then, a big thing in real world is cache performance. So do you guys sort of know about caches? How that works? So just like, briefly, caches, like, whenever you like look something up in memory, because so say you have like a really old like hard disk that spins at like, whatever the spin rate is, getting something from it takes like, a couple milliseconds. So what computers will do is whenever you get something from like a hard drive, it'll save it to a cache, and then like looking something up from a cache takes like, say, nanoseconds compared to like milliseconds to find from a hard drive. So it's more efficient to have stuff in the cache, and like that's why programs will optimize for cache performance. So you can do stuff like loop unrolling, where instead of, or actually I think loop unrolling goes into like a different category. So I'll come back to that. But like, for example, if you have, so what computers will generally do is once you make like, a hard drive hit, it'll move an entire section of memory into a cache. So then if you look at like the next, so if you look at like memory address 1, it'll like save memory addresses 0 to 5. So then if you make like a sequential access to memory address 2, so if you have like an array of contiguous memory, then like memory address 2 is already in the cache. So looking memory address 2, 3, 4, and 5, it's like a lot faster than just like, going back to the hard drive each time. So like having sequential memory is something that like makes your programs faster in the real world that like, algorithms might not account for. Back to loop unrolling though, so like what that is like each time you have a branch, so each time you have to like check an if condition. So for example, a for loop, each time like the for loop runs, you have to check if like the condition for the for loop is set, which each time you do that, you lose a few cycles because of how pipelining works, which is something you learn in 233, but you just have to trust me on that. So basically, ifs are not efficient, right? So then, say I have like a loop that says like, okay, for I is equal to 0, I goes to like 20, I plus plus, and then like, I plus equal to 1. It's actually slightly faster to make it so for if I is equal to 0, I is smaller than 4, so I is smaller than 20, I plus equal to 5, and then just do the add operation 5 times. It's actually slightly more efficient to do that. And it's also, it makes your binary bigger. That's like, real world trade-offs. And then when you get to like, if you get to 241, that's when you learn about like multi-threading and like having extra threads and whatnot, and that makes things a lot faster. So like, there are a category of problems called like embarrassingly parallel problems, which basically mean that it's like it's trivial to like outsource it to multiple threads. So does anyone have like any thoughts about an embarrassingly parallel problem? For example, if I wanted to crack someone's password, I could, have a list of passwords to try and just go through one by one and do it. Or I can have like 5 threads and try 5 passwords at a time if I have like the password hash. So that's an example of like an embarrassingly parallel problem where like each problem is discrete and can be run like, separately. So another one is, for example, serving content on a website. So say like 5 people try to load an image on a website. It's better to like create 5 threads and send an image to the people on each thread than like have 1 thread send 5 images out, because that takes 5 times as long. So in the real world, there's a lot of like hardware-specific optimizations you can do that sometimes make your algorithms like more efficient than like theoretical guarantee, or not more efficient, but like generally faster than like what you would theoretically guarantee. And it's like very easy to get caught in, oh, let me make this like algorithm faster by like doing all these like techniques, where in reality you can also just like do other optimizations. Are there any questions about this section? All right, so the final thing I want to talk about is interviewing. I know you all had like interview midterms in here. Hopefully that went well for you guys. And also like, hopefully that was like a good experience, and it will like help you in the future if you like do coding interviews or experience anything like that. There's just some general like tips about how to interview better that probably should have been given out before the midterm, but here we are. So for the future, here are some steps. So I'd say there's actually a step 0, which is do like research beforehand. So if you know you're applying for like a more low level role, maybe like read up about optimizations you can do versus if you're just doing like a general like front end interview or something like that, where they probably won't quiz you on like cache optimizations. But then when you get into the interview, number 1, you should always listen carefully to the problem. So you should always like listen to the interviewer and then ask questions if anything is confusing, right? Sometimes like interviewers will make things, they'll like actually like give you less information than it's necessary, because they want you to ask questions, because like asking questions is now a skill they test for. It makes you a better worker. So then, after you like understand the question, you should draw out an example. So like, draw out some like trivial examples. If it's like, for example, in the interview midterm questions, it's like, multiplying a list together. So, like just like write out a sample list and like see what that looks like. People like seeing like thought processes drawn out, which is good. And then always come up with a brute force solution first. You don't have to like write it down right away, but always just sort of vocalize like what you're thinking. Just like, oh yeah, like a naive solution would be like X, Y, and Z. But then like, in order to improve it, then you would start optimizing. So you can like, think about what would make your thing faster if you wanted to like, save, memoize some data, which basically means just like save things. There's a bunch of like techniques you can use to optimize that I won't get into because like it just varies per problem, I guess. So then like, once you like come up with an algorithm that you're pretty confident in, just like take a step back and think about it. And like think about like, what it is exactly you're trying to do before you start coding it up. And then once you do that, just code it, because then it should be like fairly easy at that point. And then always remember to test like edge cases at the end, because interviewers like, or some interviewers like tricking you. Others like, don't really care. But it's always good practice to like test edge cases and make sure everything works properly. All right, any questions? I'll take that as a no. So.
Just be a second setting up. Feel free to grab some more cookies or.
Yeah, you guys can totally, sorry, not to interrupt you, but you guys can totally grab Oreos if you want. They're up front. Or we can pass them around too, whatever you guys prefer. Actually, no, don't be lazy. Come up here.
Test. All right, if we're all ready to start, so hello everybody. I'm Kyle. So I'm a sophomore in math and computer science. I'm involved in all the RSOs listed here. I am a course developer for 125, and we have just released the final project, which is an Android MP. So we figured this would be a good opportunity to reach out to you guys and give you a chance to learn some basic Android development and UI design. I have an excellent hat collection, and those are my adorable little puppies on that one's first birthday. So Android at a very high level absolutely dominates the marketplace. 85% of smartphones today run Android or some version of Android. They are comparatively inexpensive. So the top of the line Android phones, so that's the S9, that is the Pixel 2, are 70 to 85% of the top of the line newest iPhone. And there are tons of much cheaper alternatives as well. And they can be developed on any computer operating system. So that is Windows, Mac, Linux, etc. Whereas for iOS and other platforms, you have to be on that specific operating system to do that. And in general, the hardware is very good. There have been some snafus in the past, I'm sure you've heard of, a few years ago with the Note 7. But yes, they are also pretty good hardware, all things considered. So today we'll be going through very quickly the technologies that Android uses, Android Studio, using it, navigating the interface, and the real world of Android and mobile development. So the technologies involved. Java code, you should be well versed or familiar with. Very popular choice for intro computer science classes, very easy to pick up. There's a great community. It's been around for years and years, so lots of APIs and documentation already exists that you don't have to be asking on Stack Overflow. A guide already exists with video tutorials, and companies use that hardware or that software already. And if you're in 125, we have been teaching it for full semester now. The user interface uses XML. So that is a markup language. It is not a programming language. It looks a lot like HTML, and it acts a lot like JSON. It is messy. It is hard to write by hand. You should not write it by hand. There are tools that are available for you not to have to do that. But it is very powerful in developing all these things. And there are lots and lots of hardware platforms that you can use that implement Android for when you write your Android. So, some of the hardware. The flagship lines I mentioned earlier are slightly cheaper than the iOS alternatives. They have most of the same features, so that is, the capability to plug into virtual reality. They have GPS, they have, tilt controls, sound, video, these interactive tools that you usually don't have in your bare bones Java application. There are cheap alternatives as well, so there are still phones that have physical keyboards that you can get for, $150, $200 that still run the newest Android operating system if you're just looking for a device to test and you like to have your iPhone as your personal phone. Tablets and watches do exist. They're mostly for developing, but some of them are like consumer grade, enjoyable pieces of software. If you are a big dev and you want to have your own apps on a tablet or watch, you can absolutely get one of those. And then virtual reality. So this actually sets it apart from iOS quite a bit. The ability to put a phone into a low budget virtual reality headset is very powerful. And Android has been it has really capitalized on that opportunity. And there is very good virtual reality support if you want to develop one of those apps. Android is usually a very good choice. And now the software. So all the software in Android are named after some kind of sweets, starting with cupcake, donut, and all the way up to Oreo, which is why we have a bunch of Oreos here today. Oreos was released in November of 2017, so very, very recent, and it is very powerful. There's a lot of security, communicability with different APIs, and new features that we really we're looking for and enjoy having in this very brand new software. So yes, the new software is awesome, but a lot of people don't actually use the newest operating system. So old phones don't support the newest necessarily. So you can actually see this graph. I can read these off for you. The big red bar on the left is actually 6.0, which is Marshmallow. That is 2 versions behind, which in iOS that's like jarring. You're 2 system levels behind. But the backwards compatibility is so good with Android that actually isn't a big deal. And as long as you have all the features implemented in the operating system minimum, you can use it for any operating system beyond that. So I'll do an example later, and we'll actually support everything up to 5.0 and back, which are the blue bars as well. If you're curious, the left blue bar is 5.1, the right one is 5. The left green bar is 7.0, the right green bar is 7.1, and the purple is actually 4.4. That's all the way back to KitKat. Yeah, Android started in the late 2000s as the iPhone was getting more popular and the modern smartphone was born. Android operating system came up to accommodate that. So some very quick key components. This is the Android lifecycle. I'm going to go over the bare bones, what you need to know about it. All of this is online and very well documented. If you want to make a nice, big, robust app, you should be using more than just the ones I'm looking at today. So onCreate is a lot like the main method that you might be familiar with in Java. So that is every time that you start your application or your activity, you enter onCreate. So if you need to set up any global fields or class fields, you should do it in onCreate. Keep track of your views and values and such in onCreate as you start, because you are guaranteed to hit that before you do anything else. In onPause and onResume, anytime that your app leaves the screen, so that is, you open your tab window to close a bunch of old apps, you switch to another app, you get a phone call, and your app disappears so that you can answer whatever phone call is coming up. OnPause will be called, so you can save the state of your app without losing any information. That is before and quick enough that your other activity has the chance to run. So OnPause is called for you for that convenience, so you don't lose whatever progress you have in the app. And paired with that is onResume, where you can take that state and draw it back to the screen, where you can pick up where you left off. So the code versus the user interface. The code and the UI are kind of separate. You have to know how to communicate between them in order to leverage them very well. So the Java code, we've preached it in 125, but object-oriented programming is very important here. If you don't use it very well, you will not be able to read your code, hours after writing it, because a lot of it is connected calls, and they're not, sequential like an MP might look like. And along those lines, knowing when, how, and who executes your code is important. So a lot of the functions are callbacks as soon as something happens in the UI. So knowing actually when this code is going to be run makes it much simpler for knowing exactly what you need to do, so you're not wasting time or lines of code doing something you don't need to be doing. They're very well documented, so if you are not sure when or how something is working, Google it. Developerandroid.com is awesome. Very good resource for when you don't know what you're doing. The UI, the XML is mostly auto-generated by the design tool in Android Studio. We can look at raw XML, and it's good for error checking, but you shouldn't really write it. You'll see why. It's very verbose, kind of messy looking, not fun. The things you will have to do or see are the callbacks to the code. So seeing where onClick points to in the code, you will see that in the UI, in that interface. So you need to know where that is so that you can communicate with your code and actually get anything done. And then making use of the emulator or a device that you plug into your machine so that you can actually view your design as it appears on a device is very, very useful. Do it often. It doesn't cost anything. It's surprisingly interactive and quick. Highly recommend doing that as you're designing or testing your app. So I'm going to hop into a quick demo of Android Studio. Here are some of the things about Android Studio to know. JetBrains, so it's a lot like IntelliJ, and in fact they're both Java, so that's the best comparison. So it comes with all these nice features you might expect, and the emulator platform, which we'll go through, is very useful for this testing purpose I just mentioned. So when you first boot up Android Studio, yours will look exactly like this, except these will not yet be here. These are other apps I have. So we're going to start a new Android Studio project, raw here. So we're going to do, I'm going to set this down. I'm actually just going to talk without the microphone just briefly so I can actually type very fast. All right. So I'm going to call this live demo application. And we're going to do mostly defaults. You can see that this is Lollipop by default, so it can hit 71% of devices. We'll just do an empty activity. It will generate some of the stuff for us. Main activity is a Java file, and activity main is the XML file. Those are what we will be working out of. And it will build. And it will build like this initially. kind of slowly, 15, 20 seconds of like code processing. And the first time you boot up an emulator will also be slow. It is booting up the entirety of an Android, and it popped up on my other screen. There we go. And it boots up an entirety of an Android system, so it will be a little more slow than hitting the run button in IntelliJ. I know that this isn't very clear to read, but I'm going to narrate anything that I'm doing that's important, and again, I'm going to be speaking so I can type. All right. So it auto-generates onCreate for you. It does nothing super important, but we're going to build an app that increments a counter by clicking a button. So we're talking UI to code in a very simple way to understand. So I'm just going to declare some global fields, or some class fields really quick, where we have a counter, and we're going to have a text view, which is the default how to view text in the UI. We're going to call that text view. So these are static fields. Protected by default is fine. And then onCreate, where we want to initialize things. We want to initialize these things in onCreate, so we're going to initialize counter to 0, which are starting, and text view, we're going to find the view by the ID, and we're going to look at the XML to see what that ID is. So,
Can you make your font bigger?
try
Command plus.
plus control plus, you're a good point. Wait. Okay. I'm going to keep going through this before we get to the line. So I'm just going to say counter equals 0, and text view, or sorry, lowercase text view equals find view by ID, which is going to be very useful for us, and then R is res.id for ID number, and then the name of that text view. I know by default that it's just called with text. So this is the design view that we might expect. It auto-generates this nice text box for us. It says hello world. Editing it is often as simple as clicking on this piece. Over here it says hello world. I'm going to say hello class. And you can see that automatically changed like this. And we want to add a button. So I'm going to pull a button down from this handy list of pre-built tools. And we can bound it to something in the already in there just by dragging the sides. I want to bound this equally between the sides and just under the text view. And this is the button. So we can change the name of the button to increment. And we can see this box here. It says on click. So this is where we point to a piece of code. Every time that it's clicked, some piece of code will be run. So let's write that method right now. I happen to know that the default behavior of this, or the method header to write, is protected, void. Let's call this increment, whatever the name is, and we'll pass it a view, whatever view we're currently on, and Alt-Enter will import that view.
Command Shift A. And then I think it's
Ah.
no, it's no.
I'll just narrate as we're going. So yes, protected void, whatever the function name is. Good description is always helpful, and then pass in a view object for whatever view you're currently using. We will not actually be using the view because we have access to the text view directly. But if you need to use the view, that is what is passed into this function. So just do counter plus plus to increment the counter, and then we're going to do text view, which is the text view that currently says hello class. We're going to do set text. We're changing the text to be whatever the counter is, and then we're going to go string dot value of, and pass in our counter, which is just a wrapper to convert an int into a string, and that is our function. So it is a So this is a protected void function. Takes a view in, and we can point to it because the method header has the view passed in and it's protected. returns void into here. So we can do onClick, we're going to do increment, I can spell. So yes, that seems good. So now every time that we're going to run this app, when we click increment, the text will update to be one value higher than it was before. And we initialized it to 0, so the first time we increment, it'll actually show 1, if I've done this correctly. Creating a virtual device is something you can do. It's really slow, so I'm going to skip it just because it takes a lot of time. And this is something I built for 125 debugging. I forgot a semicolon. Don't forget semicolon. And it popped up over here. I'll grab it from my other screen. Come on. And you can see it's thinking at the bottom, this spinning bar right here is the Gradle running for the first time on the simulator. I got a pop-up, it's on this screen, it says no, 0 errors, and then takes a second to think. All right, I forgot a part of this. I can't actually read it, but I have all the code. It will be uploaded to a GitHub and shared with you guys after lecture. I think I misspelled increment, and I actually can see it because I did. Nice. Then we can run it immediately off the same app. Hopefully this one will go. Fingers crossed. One last try. Darn. All right. Well, the code will be shared with you. I can't really read the font from here, so I'm sure it is a typo somewhere. I apologize for that.
Space in between the counter and plus plus.
That should be fine. That's just a style thing I have innately done. I'll find where that is and highlight it for you. This version, even though it doesn't work, I'll also upload for you. But you can go back to the slides now. So the correct code. The correct code looks like this. So we have the onCreate, we find the view by ID, we increment the counter. I have a decrement here as well. We do the set text for counter, and there's some extra stuff on the right where you don't actually use system.out.println, you use log. So logcat is very useful, and I have a nice little note there for if you guys come back to this, for debugging purposes. So this is the correct code. I will find my typo and probably put that in the Piazza post as well. Sorry about that. So to the real world, Android is the most common operating system in the world. Only very occasionally dips below Windows. So it actually is generally more popular, more devices than Windows, OS X, iOS, Linux, etc. Google reported value from Android since its birth, just over 10 years ago. $31 billion in revenue and 22 in profit. App developers as well as big companies do make a big profit on these. So if you hit it rich with your indie game, there's always there is a golden nugget here. And then big studios also do invest money into here because there is a big market for applications like this. In the real world, you obviously have some copyright issues as well. So Google's Android was found to be in not fair use of the publicly available API that Oracle provided. Sun Microsystems actually made it, but Oracle acquired Sun, so Oracle actually owns these intellectual property now. So you can read the big giant Wikipedia article on this 10-year court case. To be decided how much that they owe Oracle, but they were found in violation of it. Probably just under $10 billion. Quite a bit, you saw that it is worth quite a bit. You're fine as a developer, but it's very interesting at a large scale. Android will still exist because it is our, millions and millions of devices. But the market may change, and this is very interesting to. It's a hot button issue in the tech industry, and that's always fun to note. And then there's open source software licensing stuff. They licensed it as copyleft. If you don't know what that means, definitely worth a Google. And a lot of the stuff Google does doesn't necessarily abide by that, so there's concerns there. So very quickly, yes, iOS does exist. Shed a single tear. But there are pros and cons to doing either one. A lot of people like iOS, the view, and the Google, the kind of plainer looking design is a big choice, and a lot of people like it, a lot of people don't. There's pros and cons, big discussion, rabble. The app stores themselves are a little easier to break down. Slight differences in presentation and whatever, but publishing is usually easier on the Google Play Store, less expensive. It's a little more robust on the App Store, the Apple App Store. So you can look into those nuances. It is easier to publish an Android app, especially as an indie developer, for Android than for Apple. There are multi-platform solutions. A lot of them are like JavaScript web-based. I do not know how to do them. If you are a JavaScript developer or some very fancy tool that I do not, definitely do go down that path. But for quick hitting, from idea to application built, Android is one of the quickest development platforms and easiest to publish. Multi-platform is usually used at a very large scale by large companies or big studios. And I'll probably reference some of those in my post as well. So very quickly, this was very brief. There is much more to know. Please do go to those resources I recommended. I am not the oracle of this situation. But yes, I can take individual questions about stuff I've done or the other applications of all this. Android is promising. 125 adopted it because you can do a lot with Java just because Android exists, and that's one of the biggest positives that we have. We're really excited to leverage that in one of our intro classes. Links to all my stuff will be posted, and this is my favorite Android. I'm wondering whose yours is. Thank you guys.
Okay guys, so that's all we have for this week. Make sure to show up next week for our last lecture on data science. And then we'll have presentations after that the week following. So if you have any questions, you can come up here. Otherwise, yeah, you guys are free to go.